Next, we have the heat. Okay, the symbol for the heat is capital Q. Now, for the heat is the energy in transit. Energy in transit or on the move from one body or system to another. Because of a temperature difference between the bodies or system. Okay. Under the heat can also be negative or positive. Heat positive, that is heat added. If the heat is negative, that is heat rejected. Let's move on for the types of thermodynamic system. Number one is the open system. Okay. When you say open system, that is the steady flow system. Okay. Are able to exchange energy. Energy, which is heat and work. Heat and work. And mass can cross its boundary. Mass can cross its boundary. Number two type is the closed systems. This one is the non-flow system. Are able to exchange energy. And work. Mass cannot cross its boundary. That is the difference between the open and the closed system. This one are totally isolated from the environment. Which means there is no exchange of heat, work, or mass across the system boundaries. Now, we have the first law. Okay. We have the first law of thermodynamics. First law of thermodynamics states that one form of energy may be converted into another. Okay, next we have the steady flow energy equation. Energy um, equations. Equation. Now, what are the characteristics of a steady flow system? Number one, there is neither accumulation nor diminution of mass within the system. There is neither accumulation nor diminution of energy within the system. The state of the working substance at any point in the system remains constant. Figure. This one is the figure for the steady flow equation. You have this one is the system. So it's your height 1. This is the datum level. And is your height 2. This one is your PE1, potential energy 1, kinetic energy 1. Entering 1, you have the workflow 1, and then internal energy 1. Leaving, you have PE2, KE2, workflow 2, and ito na lang dito, U2. Okay, this one is the energy diagram of a steady flow system. Energy diagram of a steady flow system. Wait. We have also your work, produces the work. Enter is the heat. Okay. From that given equation, we can form an equation using the given. Okay. Entering, we have PE1 plus KE1 plus workflow 1 plus U1 plus the heat is equal to PE2 plus KE2 plus workflow 2 plus U2 plus the work. Okay. We have PE2 minus PE1 delta. Change in potential energy. KE2 minus KE1 plus change in kinetic energy. Workflow 2 minus workflow 1 is change in workflow. U2 minus U1 delta U plus the work. Q is equal to change in potential energy plus change in KE plus change in enthalpy plus the work. Okay, you can use this formula. You can change your workflow 1 plus U1 into enthalpy. Example. Okay, this one is from the book of Santa Maria, Thermodynamics by Santa Maria. Assuming that there are no heat effects, no frictional effects, find the kinetic energy and speed of a 3,220 pound body. Therefore, this one is a mass. After it falls, (778 feet from rest. Start with the steady flow equation. Then deleting energy terms which are irrelevant. Okay, given we have the mass of 3,220 pounds, height equal to 778 feet, and then (778 feet). Body after it falls 708 feet from rest. Required is the kinetic energy and the speed. to use the formula for the kinetic energy, which is equal to 1/2 mv squared. We have two unknowns. We have two unknowns, which is the kinetic energy and the velocity. Instead, we're going to use the formula for the potential energy in finding for the kinetic energy, which is the same as the potential energy, which is equal to mass times gravity multiplied by the height. For kinetic energy now is equal to mass, which is 3,220 pounds, multiplied by the gravity of 9.81 pounds. Okay, we're not going to use this one kasi it's under the English unit. Okay, therefore, we're going to use 32.17. 32.17 feet per second squared. 32.17 feet per second squared times the height of 778 feet. Okay, we can use your KE is equal to 1/2 mass times gravity multiplied by the height times K for the proportionality constant. Your mass is 3,220 pounds. This one is pound mass times the gravity of 32.17 feet per second squared and the height of 778 feet over your K, 32.174 pound mass times feet per pound force second squared. We cancel this one, 32.174, so that we can cancel this one, 32 pound mass, feet per second squared, Therefore, we have pound force. Okay, what is the kinetic energy? Therefore, this one is 2505160. That is foot pound force. 1 BTU divided by 778 foot pound force. Okay, now for the kinetic energy, that is equal to 3,220 BTU, which is the British thermal unit. These two are the values for the kinetic energy. Now, we can find now for your velocity, where the kinetic energy now is equal to 1/2 mass times the velocity squared. Now, we're looking for the velocity. The velocity now is equal to square root of 2 times the kinetic energy over the mass. Okay, sorry. Again. Now, we have the velocity, which is equal to square root of 2 kinetic energy times the mass. Therefore, substitute, that is equal to 2. We're going to use your foot pound force. 2 times the kinetic energy of 2,505,160 foot pound force over the mass of 3,000 of what is the mass? 3,220 pound mass. But if you can see, we cannot get for the value of your velocity. It should be in feet per second squared. Remember that pound force is equivalent to slug feet per second squared. Therefore, we need again your proportionality constant. Always include your proportionality constant. Okay, therefore, your pound force is slug feet per second squared. But the given unit of your mass is in pound mass. Therefore, we're going to use 32.174 pound mass feet per pound force second squared. Now we can cancel the units. Your pound force, then pound mass, then feet times feet squared. The unit would be feet squared per second squared. And the square root of your feet per second squared, this one is feet per second. Okay, now the velocity. Okay. Now for the velocity is equal to 223.75 feet per second. This one is the final answer. You have the kinetic energy now and the velocity. Example. Again, from the book of Santa Maria. Steam enters a turbine with an enthalpy of 1,292 BTU per pound mass and leaves with an enthalpy of 1,098 BTU per pound mass, the transferred heat is 13 BTU per pound mass. What is the work in BTU per minute and in horsepower for a flow of 2 pounds per second? Okay, given we have H1, which is equal to 1,292 BTU per pound mass. H2 is equal to 1,098 BTU per pound mass. Then heat, your Q is equal to negative 13 BTU per pound mass. Then the mass flow rate is equal to 2 pounds per second. Requirement, we have the work in BTU per minute and the work in horsepower. Okay, now for the computation, the requirement is the work in BTU per minute, the work in horsepower. Now, using the formula for the energy equation, remember, we're not going to use the potential energy, the kinetic energy. Instead, we're going to use only the heat is equal to change in enthalpy plus the work. Disregard all the others, all the other energy. Now the given heat is transferred, therefore that is negative 13 BTU per pound mass. Then your change in H, that is H2 minus H1, plus the work. Okay, now we have the work, which is equal to negative 13 BTU per pound mass minus your H2 is 1098. 1098 minus 1,292 BTU per pound mass. We can subtract now because they have the same units. This one is equivalent to work is equal to 181 BTU per pound mass. Now, the requirement is the BTU in BTU per minute. Okay, we have to multiply this one by the mass flow rate. Your mass flow rate is 2 pound mass per second. Pound mass, pound mass. But the requirement is in minute times 1 minute is equal to 60 seconds. Okay, therefore, this one is equal now to the work is equal to 362 BTU. 362 BTU per minute. 362 BTU per minute. Aha, mali. 181 times 2 times 60. Correction. 181 times 2, that is 362 times 60. The work is equal to 21,720 BTU per minute. Okay. You have now your BTU per minute. Then we have to convert this one times 1 horsepower. 1 horsepower is equal to 42.4 BTU per minute. This one is the conversion. 1 horsepower is equal to 42.4 BTU per minute. Therefore, your work now is equal to 512.26 horsepower.